maybe with your homework, yeah, with the solution of your homework. And okay, let's start. I think all of you receive my feedback, and all of you except maybe one or two people receive more than half points for this homework. Yeah, and okay, I will start whiteboard. Okay, now I show you the solution of last 3 exercise. This second part, yes. This second. X1 dot equal to x1 cubed plus x2 and x2 dot equal to minus 2x1 minus x2 in 5 degree. Okay, and here we need to find the equilibria. X1 dot equal to x2 dot equal to 0, yeah, and x1 0 and 0 equal to x1 plus x2 minus 2x1 minus x2 in 5 degree, and then we can see that here when x2 equal to 0, then x1 equal to 0. Okay, the first equilibrium point equal to 0, 0. Okay, and when we calculate the another 2 equilibrium points, we receive one moment. Okay, we can use MATLAB, for example, and x2 equal to something like minus 1/2 14 and 8/14 and x3 equal to something like 1/2 8 and minus 8. Okay, something like this. And let's calculate the equilibrium. Sorry. Okay, equilibrium df dx equal to 3x1 squared 1 minus 2 and minus 5x2 in 4 degree. Okay, and Then for 0, 0, for example, for 0, 0, it's equal to 0, 1, minus 2, 0, yeah, and then we found minus lambda plus 2 equal to 0. Okay, lambda squared equal to minus equal to minus 2, yeah, and equal to minus 2, and lambda 1, 2 equal to plus minus g. Okay, real part is 0, and we can decide about the stability under the first Coulomb method in this case. When we put the another two equilibrium to this Jacobian, yes. Oh, sorry. Sorry, I have some problem with this whiteboard. One moment, please, because I have some problem with whiteboard and I try to reload. Okay, and the eigenvalues of the second equilibrium point approximately minus 8 or 9 and 3, and the second one, the second eigenvalues is positive, and so equilibrium point A2 is unstable, and the third one is the same, yes, is the same eigenvalues, so the third equilibrium point is also unstable, yeah, and I tried to start whiteboard and I don't know why I can't. Oh, now it's stopping. Okay, and the next exercise 3, and you need to check the stability of the origin, the stability of the equilibrium points, and system described by the equation x1 dot equal to minus x1 cubed plus x2, and x2 dot equal to minus 2x1 minus x2, and this system has only one real equilibrium point, okay. You see whiteboard now?
Yes.
this third exercise, system described by x1 dot equal to minus x1 minus x1 cubed plus x2 and x2 dot equal to minus 2x1 and minus x2 and x1 dot equal to x2 dot equal to 0, and then we can find that only one equilibrium point, and some people solve imaginary equilibrium point, yeah, and you don't need solve any you need to solve only a real equilibrium point, because as you know, for example, when we solve some physical system, equilibrium point is always real. Yes, for example, I don't know, when we have some position and some speed, yeah, position is x1 and x1 dot is a speed, yeah, and x2 dot x1 with 2 dot is accelery, yeah, and so on, yeah, and you don't need in the exercise solve complex equilibrium points, okay? Because maybe 10 people do it, yeah, in homework. Okay, and now we know that x1 equal to 0, 0, and the Jacobian df dx equal to, okay, minus 1 minus 3x1 squared and 1 and minus 2 and minus 1, and okay, it's in 0, 0, it's equal to minus 1, sorry, minus 1, 1, minus 2, and minus 1, and then we need to find eigenvalues, minus 1 minus lambda, minus 1 minus lambda, and minus 2, 1 equal to 0, and now, okay, it's 1 plus lambda plus lambda plus lambda squared plus 2 equal to 0. Okay, lambda 2 plus 2 lambda plus 3 equal to 0. And in this step, we can say that this system is stable. Yes. Well, not only stable, but you can say that because here all coefficient is positive, and then this system is exponential stable. Yeah. Well, someone write in homework that it means when, for example, when we calculate the eigenvalues, then we found that lambda 1, 2 equal to minus 1 plus minus square root of g. Yeah, and okay, it's stable focus. We know that it's stable focus, but many of students write only that this system is stable. Yeah. Okay. for example, when you will solve the tasks from writing test, then you need exactly say which kind of stability of the system in this case, yeah. And when we have this coefficient positive here, yeah, then we can say that this system, because the real part of eigenvalue is negative, then we can say that this system is exponential stable, yeah, and local. Why local? Because only in this, but I think this system is global stable, yeah, because only one equilibrium point here. Okay, but we analyze only with indirect Lyapunov method here, and the question is if this is stable or not, and why. And on this step, yes, you can say, okay, it's stable, yeah, because the coefficient is positive, and we know that if coefficient is positive, then this system, then the real part of eigenvalues is always negative, and then this system is local exponential stable. Okay, any question? Okay. I hope you hear me. Okay, and the last example from homework, this number 4. X1 dot equal to minus x1 cubed plus x2 cubed plus a x1 and x2 dot equal to x1 cubed minus x2. Okay, and here okay, here we need to analyze the stability of the origin, and you don't need find the equilibrium point in this exercise, yes, in this task, and you need only calculate Jacobian, because here you need to use the first Lyapunov method. Okay, df dx equal to minus 3x1 squared plus a and 3x2 squared and 3x1 squared and minus 1. Okay, and origin is 0, 0, yeah, and the Jacobian equal to a 0, 0 minus 1. Okay, and we know that a some parameter in R, and that's found the Jacobian, sorry, the eigenvalues, a minus lambda minus 1 minus lambda equal to 0, yeah? And from this step we can say that, okay, now we know that lambda 1 equal to A and lambda 2 equal to -1. Yeah. Any question on this step? Because here is equal to 0 or this part equal to 0, yeah? And then it's equal to 0. Okay, lambda 1 equal to A, lambda 2 equal to -1. And because some of students very carefully calculate the eigenvalues, maybe with MATLAB or something like this, and make a mistake. Yeah, and you can see that lambda equal to A and lambda equal to -1. Okay, when A less than 0 and lambda 1 equal to 0 and lambda 2 equal to -1, what we can say about the stability of the origin? It's asymptotical stable. Maybe we can say more about the stability of this equilibrium point. Okay, this is asymptotical stable. Vertical. Okay, this system in equilibrium is asymptotical stable. Okay, a local asymptotical stable. But I say that if real part is less than 0, that we can say that this system is exponential stable. Okay. Okay. You can say, okay, this asymptotic, it's right, but if system exponential stable, then this system is asymptotic stable, yeah, and Lyapunov stable, or stable, only stable, yeah. This is some more, yeah, and then asymptotical stable and some easy stability, yeah, and so on. And Lyapunov stable is the worst case or something like this, yeah. And we know that this system, because for example on test or on exam, Professor Chirikowski can ask you if you can characterize this kind of stability, yes, and you can characterize easy when real part less than 0 or negative, then this system is local exponential stable. Okay, local exponential stable. Okay, the another case, lambda 1 equal to A greater than 0 and lambda 2 equal to -1. What we can say about the stability of this system when A greater than 0, when A positive?
It's unstable.
Okay, it's unstable. We know, thank you. We know that this kind of, this is unstable because one eigenvalue negative and the second one is positive and it's unstable. And we know that this is a saddle point. Yeah, you don't need know if this saddle or not saddle, but only for your information. Yeah, and okay, unstable, and when lambda 1 equal to A equal to 0 and lambda 2 equal to -1, what we can say about the stability? Someone know?
we cannot decide with the first Lyapunov method.
Okay, thank you. Okay, we can decide. Yeah, can't decide. Okay, this is a full answer. Yeah, for the last exercise, because someone only writes that when a less than 0, that system is stable. Okay, I know that maybe someone means that when a greater than 0, that the system is unstable. Yeah, and I penalize with 5% for this exercise when someone do not explain when a equal to 0 if it's stable or unstable. Okay. Okay, and on the test, you all. I know now that in test one of tasks with some parameter, yeah, a, and you need to decide when it's stable, when unstable, and why. Yeah, and you need to know that you always need to solve this. For example, a equal to 0, something like this. Yeah, and a greater than 0, a less than 0, and then you can decide about the stability. Okay, any question? Okay. Okay, thank you. Let's solve some another systems. Okay, here I want one moment. I want to find the system from your lecture. Okay, this one. Now we solve a system from lecture number 3, page 9. And this x1 dot equal to x1 minus x2. Okay. Okay, this system x1 dot equal to x1 minus x2 minus x1 and x1 squared plus x2 squared and x2 equal to x2 plus x1 minus x2 and the same x1. Okay. When we apply the first Lyapunov method, what we can say about the stability of equilibrium point in 0, 0 in origin? Okay, I try to calculate. Is dx equal to x1 1 minus 1 1 and 1, yeah, because it's in 0, 0, yeah, and okay, and let's calculate the eigenvalues. 1 minus lambda, 1 minus lambda, and plus 1 equal to 0. Okay, and this 1 minus 2 lambda plus 1 equal to 0. Okay, and I think it's correct, this calculation. Okay, and lambda minus 2 lambda plus 2 equal to 0. Okay, lambda 1, 2 equal to. Do you have answer? Lambda 1, 2 equal to. Okay.
I think it is 1 plus minus 1 J.
Okay, 1 plus minus J.
One imaginary unit, one J. Yeah.
Okay. Okay, and what we can say that this we can say that this system is unstable. Okay, because both of eigenvalues, the real part of both eigenvalues, greater than 0. Yeah, this is unstable focus. We know that if some imaginary part, yeah, then this is unstable focus. When only real part, then it's unstable node. Okay, unstable focus. And now I switch to MATLAB, and one moment. I only want to okay, I run the simulation of, okay, and now I show you the result of the simulation. Okay, I don't know if you see. One moment, okay, I share the screen. Maybe it's really better, yeah. And you can see that vector field of this system is like this. Yeah, you can see this figure.
Yeah, we can see
Okay.
figure 1.
Okay, and you can see that this is some stable cycle. Yeah, and here different initial condition. For example, we start with x equal to 0.001, and after some time this converges to this limit circle. Yeah, and when we start outside, when we start on the circle, for example, this maybe it's very close, 1, x equal to 1, and then it stay on this circle. And when we start outside of this stable circle, then it's going to the stable and stay on this. Yeah, and it's very interesting that this system is unstable, this origin, yes, but system not unstable, yeah, because the equilibrium point is unstable, but when we I think when we apply the second Lyapunov method, we can found some restriction, and okay, and we can change the coefficient here. This for example 4, and then it will be much less, and you can see that when we start, we always stay on this stable circle. Okay, and we can solve another interesting example with with unstable focus maybe. Okay, I come back to whiteboard. Sorry. Okay, I finish. And now whiteboard. And we need okay, and now okay, and now we solve the next system. X1 dot equal to x2 and x2 dot equal to minus x1 plus x2 and 1 minus 3x1 squared minus 2x2 squared, and this system has only one equilibrium point in the origin, and let's calculate the equilibrium. df dx equal to 0 1, okay, minus 1 1, and the eigenvalues is equal to lambda 1 2 equal to 1/2 plus minus 2g. Okay, the region is unstable focus, and let's make a vector field. I only need to change my MATLAB code, and we can see how the system the behavior of the system. And okay, one moment. 3x1 squared minus 2 minus x2 x 22. X2 x1 x2 minus. Okay, and now I can show you the result of the simulation. Okay, it's like the previous example, yes, and when we start near the origin, then the solution converges to stable limit cycle. Yeah. Okay. Okay, and okay, and now let's consider the system. Okay, consider the system x1 dot equal to arctangents arctan x1 plus x2 dot equal to x2 plus x1 plus x1 squared minus 1 times x1. Okay, and let's determine all equilibrium points and their local properties by the first Lyapunov method. Okay, we can find the equilibrium, then x1 dot equal to x2 dot equal to 0, and when we solved, we can find that first equilibrium point x1 is equal to 0, 0, and x2, 3 equilibrium point equal to plus minus 1 minus plus 1. Okay, and calculate the Jacobian. df dx equal to this arctan, this 1 divide x1 plus x2 cubed plus 1 and the 1 divide x1 plus x2 plus 1, and this one is three x1 squared plus 1 plus minus 1 minus 1 and plus 2x1 and plus x2 and here it's x1 only. Yeah, because it depends on x2, x1, x1. Okay, and now Jacobian the f dx in 0, 0 equal to 1, 1, 1, 1, 0 plus 1, 1 divide 1, 1. Here 0, 0 is 1 divide 1, 1. Here it's 0, minus 1, minus 1. And here 0 is 2. Okay, and okay, we can calculate this eigenvalues. Lambda 1, 2 equal to 1/2 plus minus g. Okay, and as we know, this is unstable focus. Okay, and the second equilibrium point, df dx in 1 minus 1 equal to 1, 1, and here it's 3 minus 1, 2 plus 2, 4, and minus 1 is 3. Here 3, and here it's x1 equal to 1. Okay, and when we calculate here lambda 1, 2, the eigenvalue is equal to 1 plus minus root of 3 is a, we know that this is can someone want to calculate this eigenvalues of this matrix? The f dx minus 1, 1 equal to 1, 1, 1 minus 1. Okay, here it's 1 minus lambda, 1 minus lambda, minus 3 equal to 0, and 1 minus 2 lambda plus lambda squared minus 3 equal to 0, and lambda 2 minus 2 lambda minus 2 equal to 0. And the last one is lambda 1 minus lambda minus 1 minus lambda and plus 1 equal to 0. Okay, and minus 1 minus lambda plus lambda plus lambda squared plus 1 equal to 0, and lambda 2 equal to 0. maybe something like this, and we can decide about the. Okay, you can finish this task at home, yeah, and let's calculate some another example. Okay. Okay. Okay, x1 dot equal to minus 2x1 plus x1 cubed and x1 dot equal to minus x1. Okay, and we need to prove the stability of this system. And we need to check if this system is local or global asymptotical stable. Okay, and use the first Lyapunov method. If dx equal to minus 2, 0, in 0, 0, minus 2, 0, and minus 1, 0. Okay, and this is x2, sorry. 0, minus 1. Okay, and in 0, 0, it's the eigenvalue is lambda 1 minus 2 minus lambda 1 minus lambda 1 lambda, sorry, okay, minus 2 minus lambda minus 1 minus lambda equal to 0, lambda 1 equal to minus 2, and lambda 2 equal to minus 1. And we can say that this system is, what we can say about this system now? We can say that this system is local exponential stable because the real part of eigenvalues lambda e is negative, and let's apply the second Lyapunov method. Okay. X1 dot equal to, sorry, v from x equal to 1/2 x1 cubed plus x2 cubed, and v dot equal to x1 dot plus x2 dot, it's equal to x1 and minus x1 minus 2x1 plus x1 cubed and plus x2, and here it's minus x2. Okay, and it's equal to minus 2x1 cubed plus x1 4 degree minus x2 squared. Okay. And what now? The system is stable or not? Can we decide about the stability? Any idea?
No, maybe only local stability.
Okay, can I do something with this v dot from x? I think we can try to rewrite it. It's equal to, sorry, equal to, okay, equal to minus x1 squared, and here it's 2 plus x1 minus, sorry, not plus but minus x1 cubed. Yeah. And minus x2. And now we can see that in the case when, what we can say about the stability now? Okay, we need this part is less than 0 and this part is less than 0, yeah? Okay, we know that always for all x2 not equal to 0, this part is less than 0, yeah, this part. And now we need to say when okay, when this part is less than 0, we need this part is need to be positive, yeah, and this part needs to be positive. Yeah, you know that 2 minus x1 squared is greater than 0, then it works. Yeah, and know that
x1 smaller than square root of 2.
x1 more or less, I think, yeah. One more, please. x1.
x1 smaller than square root of 2.
Okay. And maybe it's something like this. Sorry. Because yeah, I think now it's correct. Yeah, it's correct.
Yes.
Yes.
Yeah. Okay. Okay. And now we know that this system is local, asymptotical stable, and for all x2 not equal to 0, and for x1 greater than root of 2 and less than root of 2, minus root of 2 and less than root of 2. Okay, and something like this. Yeah, and we prove the asymptotical stability in not near the origin, but in wide region. Yeah. Okay. Let's do it. I need some another. Okay. x1 dot equal to x1 cubed minus x1 x2 squared, and x2 dot equal to minus x2, and prove that the origin is global asymptotical stable. And we need to apply only the second Lyapunov method because we need to prove the global stability of this system. And second, this direct Lyapunov method. Okay, and let's take v from x, this classical 1/2 x1 squared plus x2 squared, and v dot from x equal to x I'm sorry, I have some problem with I need to reload the whiteboard. Okay. Okay, 1/2 x1 x1 cubed plus x2 squared v dot from x equal to x1 x1 dot plus x2 dot, and it's equal to x1 minus x1 cubed minus x1 minus x1 x2 x2 squared and my plus x2 minus x2 is equal to minus x1 in 4th degree minus x1 cubed squared x2 squared and minus x2 squared. Okay, and what we can say about the stability of the system? For all x not equal to 0, this is less than 0, okay? And therefore, the origin is global asymptotical stable. Not origin, but system. Yeah. Okay, and the next example.
One question.
Okay.
Where is the minus in the line with v dot of x equals, and where's the minus in front of x1 cubed from?
Sorry, I made a mistake here. Yeah, with minus. Thank you. Yeah, minus x1.
Okay.
Okay.
Okay, thank you.
Okay, and now we make some interesting example. Let's design the feedback controller. The system is x1 dot equal to x1 cubed minus x2 x3 x2 dot equal to minus x2 in 5 degree plus x3 and hence x1 and x3 dot equal to x1 x2 squared plus u. And we need to design this u that renders the origin global asymptotical stable. Yeah, and we need to design this u. Okay, what we need to do? We can use the Lyapunov function here. Let's use v from x equal to 1/2 this classical Lyapunov function x1 squared plus x2 squared plus x3 squared, then v dot from x equal to x1 and x1 dot plus x2 dot plus x3 dot equal to, and now okay, and now it's equal to x1, this minus x1 cubed minus x2 x3 plus x2 and minus x2, and here one moment. Okay, x2 minus x2 in 5 degree plus x3 tangents x1 and plus x3 x1 x2 squared plus u, and it's equal to minus x1 in 4 degree minus x1, sorry, plus, not minus, but plus x1, x2, x3, and plus x2, sorry, minus, we can directly write that here it's minus x2 6 degree and plus x2 x3 tangents x1 and plus x3 x1 x2 squared plus x3u, and what's now? Okay, it's equal to x1 in 4 degree, this x1, then this minus x2 in 6 degree, and now you can see that here it's x3, 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 and x3, and plus x3, okay, and here it's x1, x2, this part, yeah, and here it's plus x2 tangents x1 is this part, yeah, and from this part it's plus x1 x2 squared, okay, and plus u, yeah. Any question here? Okay, and now we need to design this u. To render the origin global asymptotical stable. Yeah. Any idea what we need to do? Okay, here we have this minus x1 4 degree, minus x2 in 6 degree, and here we need to do something when we have this x3 in some degree, for example, in second degree, yeah, minus x3 squared. Okay, and we design this u equal to, and now cancel all these terms. x1, x2, minus x1, x2, minus x2 times x1, minus x1, x2 squared, and the last one is minus x3. Okay, and when we put this u here, then it's equal to minus x1 in 4 degree, minus x2 in 6 degree, and minus x3 squared. Any question? And this is less than 0 for all x not equal to 0. And we can conclude that the origin is global asymptotically stable with this control law. Do you have any question? Okay, do you have some question about second homework? Okay, maybe today or in Monday, I put the third homework to Moodle, and I give you 3 weeks, yeah, for the solution. And this homework will be about the stability, about the calculate the stability, prove the stability via the second Lyapunov method. Yeah, and okay, if no question, I think we can finish our.
Sorry, I have a question.
Okay.
When will we have a test? The first test.
First test. I know. You know, we need to finish backstepping. When we finish backstepping, when after backstepping, we made test. We will make it. Maybe I don't know. Now it's 5th week or something. I maybe after 2 seminars. Yeah, maybe next seminars and one more, and then we make a test. Yeah, we will make a test. We need to finish backstepping because in this test you need to solve some examples with first Lyapunov method, with second Lyapunov method, and backstepping. Yeah. And now you can apply the second Lyapunov method, and this backstepping is the last step in backstepping is like here. Yeah, when you need to stabilize something, you need to put, for example, here, yeah, this u. You need to put something to cancel these terms. Yeah, this with minus, take these all terms, this one, and this one with minus, yeah, with minus, and then put something, because here x3, yeah, and you need now it's no backstepping, only design the feedback via the Lyapunov function, because we take a Lyapunov function, calculate the derivative, and then try to put something here, yeah, and for example we can put this minus x3 in 3 degree, it's okay, in 5 degree, yeah, it's okay, in 5 for example. Always this system will be stable, yeah, will be stable. Okay, if you haven't question, I think we can finish our seminar and see you next time. And if you have some question, you can write me a mail and I send you answer. Yeah. Okay, goodbye. Thank you.
Thank you. Goodbye.
Goodbye.
Yeah, thank you. Goodbye.